Okay, sorry about that. So quickly, I want you to determine the pH of this original solution. Do that now. Okay, so it looks like our quantity of X, which is equal to these two, is going to be approximately, and that would be H positive as well as F minus here, is going to be approximately 0.019, and the pH is going to be pH equals 1.7 approximately. Notice I will not be meticulous with sig figs, but you should be. When you get done with any question, when you're finally done, you go back and round. It's always useful to keep 3 sig fig digits or 4 all the way through your calculations. Okay, so you need to be aware of that. You're taking the test, minus half, minus half, minus half. I've already taken the test, so I'm not getting graded. So I'm not that concerned about sig figs. But for real, when you're done, go back and check. It doesn't take long. And just round off your number using the rules that are familiar. Okay? So anyway, here's the pH of this solution here. So it's 1.7. Be careful, this is a weak acid. Acetic acid is a weak acid. But just because it's weak, it doesn't mean you take showers in this stuff. This is significant pH, danger to skin, eyes, etc. And that's at a 0.50 big M concentration. You can imagine, what if it's highly concentrated? If you go up to 2 molar, 5 molar, 10 molar, that's more dangerous than, let's say, a 0.20 big M HCl concentration, or about the same in terms of danger, in terms of its caustic effects. So just realize that. Anyway, there's our pH. Now what I want to do is add a soluble salt. So we're going to add sodium fluoride. Solid salt, sodium fluoride, and that's going to ionize 100%. So we're going to go to Na positive plus F minus. Now how much are we going to add? Let's add 21.0 grams of that. And the first thing I want you to do is determine the molarity of this solution based on this initial amount and based on the volume there. Marcus said go. Go. Don't be messing around. Okay, so it looks like let's convert grams to moles, and when we convert grams to moles, we're going to have approximately 0.50 moles, and that's going to get 0.50 moles here plus 0.50 moles there. Notice 0.50 moles here. Let's divide that by our concentration. So let's get, let's divide that by the total volume. So we have 0.5 divided by, really don't need to use a calculator here. This is going to be a 1.0 molar solution. So the molarity of F minus here is 1.0 big M solution. Of course, when these species enter this solution, the sodium will act as a spectator ion. The F- concentration will rise. We will disrupt that equilibrium there. And of course, we're going to shift. The stress is here, so this concentration goes up. Look at that. A lot higher than it was a moment ago. Much, much higher than it was a moment ago. And then we're going to be shifting in this direction. We'd expect the H positive to go down. We'd expect the pH to go up. But what I want you to do now is use Henderson Hasselbach equation to calculate the new pH after the addition of this amount, which led to a change in concentration of this. One thing I will say, when we add that solid, let's assume the little bit of water displacement is negligible and that volume has, it's going to rise a tiny bit, but let's assume that's negligible. We'll just keep that number instead of increasing it by a small factor. So go ahead and go. New pH of this buffered solution. Okay, pH equals pKa plus log of weak acid conjugate base concentrations. Weak acid conjugate base concentrations. Notice we're given the Ka, so we can determine the pKa of that. Notice we've determined the initial amount of our acid, and we've determined the amount of the conjugate base after we've added the salt. Again, we had to figure out the moles and then divide by 0.5. So divide by 1/2. Anyway, here we go. Let's see what we got here. We'll take the pKa, 7.1 for negative. And we've got a value here of 3.15. And then let's look at the ratio here. It looks like our F concentration, our conjugate base, is 1.0. It looks like our HA is 0.50, big M. That value is going to be equal to 2. We'll take the log of that. And it looks like the log of that is 0.301 plus 3.15. And let's get a pH value. And it looks like our pH is going to be 3.5 after the addition of that conjugate base. One thing I want to point out here is obviously the ratio here is really important. In this particular case, the ratio here is above 1, so the log of any number above 1 is going to be a positive number, so that positive number we're adding to the pKa. If this ratio is a negative number, or let me restate that. If that ratio is below 1, then the log value will be a negative number. So if this ratio is below 1, the log's going to be a negative, and then we'd be subtracting from that value. What if this ratio is 1? If this ratio is 1, the log of 1 is 0, and then the pKa would equal the pH. So it's helpful to kind of keep those sign conventions in mind when you're using this equation. Does it make sense that if the ratio of conjugate base to weak acid is over 1, does it make sense that the pH is going up. So notice, that's a positive value. And let me reiterate here, so that's the log. I took the log to get that number. I've got the log here. So did it make sense that the pKa value is going up when that amount is greater than 1? Of course it does, because you've got the conjugate base in the numerator and you got the weak acid in the denominator. If this goes to 3, 4, 5, 6, that's going higher, 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 because conjugate base is increasing. So when conjugate base increases, you should get a higher and higher pH. On the other hand, if this number is below 1, let's say this value is 10 and this value is 1. If you take the log of that number below 1, then this, of course, would be a negative value then, and we would be getting lower. The pH would be getting lower than the pKa. And that makes perfect sense, because if you have a 10-to-1 ratio of acid to base, the pH should be getting lower because of that excess amount of acid compared to base. So, you need to look at this. You need to practice some. I'm going to send out homework, and I'm going to post another video on determining the appropriate pH of a buffered solution. So, I'm going to take a break, get some coffee. It's the fuel of education, you know. And I'm going to get back and we're going to talk about creating a buffered solution of a particular pH.